Okay, so in this series, this is the second video. Um, in the previous video, we have discussed what is sampling. Basically, uh, there is a population, and population is the big set of all units, and from that population, to measure the character of the population, we will take some samples from the population. Sample is nothing but the subset of population. Now, let me discuss what is parameter and what is statistic. A numerical measure, that means any measure of the population, is actually parameter. And for example, population mean, which is denoted by small m, population variance, and any measure of the sample, that is a smaller one, sample, is called statistic. Sometimes it is very tough to uh, decide the features of the population on that situation. For most of the cases, we will take some samples from the population, and this will help to make the decision about the population. Of course, a carefully selected sample may be expected to possess the characteristics of the population. We will discuss this theory basically from the samples. Uh, the chapter we will discuss is estimation of the parameter. Now the situation is uh, capital X1, capital X2, dot dot capital Xn, the set of population of size n. That is, it's a complete list of the units of the population, and from that list we will take a sample of size n, namely small x1, small x2, dot dot small xn, and where theta is a parameter of the population. So what is parameter? Parameter was the measure of population. So our problem is to replace theta by some suitable statistic. What is your statistic? Statistics is a measure of sample, any measure of sample. Now, there are two type of estimation. One is point estimation and other one is interval estimation. Our main focus will be point estimation. Okay, so what is point estimation? So as I already told you that theta was a parameter, so we will replace that theta uh, with the with some suitable statistic theta cap. Theta cap is a function of x1 x2 dot dot xn, that is the sample. That is, theta cap is a function of x1 x2 xn. As I already told you that theta cap is a statistic. In case of interval estimation, the value of theta will lie between the statistic theta 1 cap and theta 2 cap. Basically, we will have an interval theta 1 comma theta 2. This is called confidence interval. We will discuss it later. First of all, we should know that a good estimator, maybe it is point, maybe it is interval, a good estimator must have these following characteristics. Number one, it should be unbiasedness, consistency, efficiency, and sufficiency. Our main focus will be unbiasedness. So what is unbiasedness? A statistic, capital T. What is capital T? It's a statistic. And what is statistic? Statistic is a any measure of the samples. Sample, in this case, sample of size small n. Statistic capital T is called unbiased estimator of the parameter theta if the expected value of the statistic is equal to the parameter. In mathematical way, we can say that expected value of t equal to theta. And of course, what is consistency? The statistics Tn, where n is the sample size, is called consistent if for epsilon greater than 0, probability Tn minus theta less than epsilon, the probability of when n tends to infinity, when the sample size of the sample is bigger enough, will be equal to 1. Equal to 1 part is missing actually. Equal to 1. This thing will be equal to 1. Here we will discuss some important result. The first result is the sample mean is an unbiased estimator of the population mean. So let me first of all uh, understand the question. What is sample mean? Sample mean the measure of the sample, that is it is a statistic. And what is population mean? Population is a measure of the population, that is it is parameter. So one is statistic, another one is parameter. So the question is, sample mean is unbiased estimator of population mean. What is the definition of unbiased estimator? Go back to the previous slide. The unbiasedness is actually capital T is an unbiased estimator of small theta if E of t equal to theta. That's all. Now the situation is uh, here like the previous situation, capital X1, capital X2, capital Xn is a population of size n, and small x1, small x2, small xn is a sample of size n. Obviously small n is less equal to capital N. So first of all, we will calculate E of x1. So you should know, you should remember that how to calculate expectation. It is x into probability of capital X equal to x. That is, choose all possible of x and uh, multiply the probability of x. So all possible x1 means it is a complete list of the population. That means it is nothing but capital X1 into 1 by n, and you know that the sample, the probability of having each unit from the population is actually 1 by n. All are equally probable. So that after all the calculation we will have it is small m, that is population mean. Similarly, uh, we will have E of x1, E of x2 and E of xn, all are equal to small m. Now here it is, sample mean. Sample mean, by our definition, this is your sample mean. So what is our target? To calculate E of x bar. Let me calculate what is the value of E of x bar. After all the calculation, you will see the calculation in the PowerPoint. So first of all, your task will be to pause the video and write everything in your copy. So it's very simple calculation. So this is equal to m. So E of x bar equal to m. This shows that it is unbiased estimator of the population mean. Another result is the sample variance is a biased. It's not unbiased. Sample variance is a biased estimator of the population variance. So m and sigma square are the population mean and variance. Their parameter, since the calculations are based on population, their parameter. X bar and capital S square are the corresponding sample mean and variance. So they are statistic. They are the calculation on the basis of the samples. So they are statistic. Now, by the previous calculation, E of x1, E of x2, E of xn, that is E of xi equal to m and var of xi, if you calculate in the simple way, this will be simple sigma square. Now we have already calculated that E of x bar equal to m, because the uh, sample mean is unbiased estimator of population mean. Obviously E of x bar equal to m. Now let me calculate var of x bar. Var of x bar is var of x1 plus x2 plus dot xn by n. Since var of ax plus b, you know from your previous probability results, var of ax plus b is nothing but a square times var of x plus b. So that 1 by n should be coming out as 1 by n square. So 1 by n square times var of x1 plus x2 plus dot xn. After all the calculation, it will be sigma square by n. Now look, sample mean is this, sample variance is this. If you calculate 1 by 1, this is s square equal to 1 by n times, by the definition we have sample variance is this, and by adding and subtracting minus m and plus m, look at the calculation properly, this will be, looks like this. I need the last expression, that is capital S square equal to the last expression. Now take the last expression and take the expectation both side. Yes, okay. After that, this will looks like this. Now see what is coming out. E of s square equal to n minus 1 by n times sigma square. So if E of s square would have been only sigma square, then we can say that capital S square is a unbiased estimator of sigma square. But what is coming out here? E of s square equal to n minus 1 by n times sigma square. So we cannot say unbiased. We should say that capital S square is a biased estimator of sigma square. Okay. If you set small s square as n by n minus 1 into s square, if you take then expectation, you can see that n minus 1 by n will be cancelled. Then E of small s square should be equal to sigma square. On that case, small s square is unbiased estimator. Now, here comes its very important topic for you, maximum likelihood estimator. So, theory portion of this maximum likelihood estimator is very large. So, we will understand this topic by solving some examples. Example 1. Find the maximum likelihood estimator of the parameter p for a binomial distribution n comma p population n comma p population for a sample of size small n. Now, in our previous studies, we already know binomial, Poisson, normal, Cauchy. We have, and of course, there are so many distributions. For all the distribution, the problem can be from any distribution. Now, I am solving this problem based on binomial. The problem can be based on Poisson. The problem can be based on normal. So, first of all, you should check how I am solving this problem. Okay, the situation is same. Capital X1, capital X2 dot capital Xn is a population of size capital N. It's a complete list, and from that list, from that population, we are taking a single sample of size n, which is x1, x2 dot xn. The probability mass function, as we already know what is probability mass function for the binomial distribution, f of xi, probability x equal to xi equal to nci p to the power xi into 1 minus p to the power n minus xi. Okay. Now we will fit a function. We will fit a function capital L. What is capital L? It is likelihood function. Remember that it is likelihood function capital L. It is product of all probability mass function. That is f of x1 into f of x2 into f of x3 dot dot f of xn. So it is just simple product. Now, for every distribution, whenever you are having probability mass function or probability density function, product of all those functions, by putting all the points available in your sample, product of all those functions will be equal to capital L, and take log both sides. This will looks like this. Okay, so log L equal to this. Now, what is our next step? Next step is what was your question? To find the maximum likelihood parameter of the parameter p, small p. So what we need to do? We need to calculate del p of log of L equal to 0. Okay. So these things, after some calculation, it is just derivative. After some calculation, we will have p equal to, what is our target? We need to calculate your p. So p equal to x bar by n. It's not over yet. You need to calculate the second order derivative, and just you should put the value of p, and after putting all these things, this second order derivative should be negative. Then your answer will be correct. So p cap will be x bar by n is a likelihood parameter estimator of small p. Let me give you another example. Find the maximum likelihood estimator of the parameter small m and sigma for a normal distribution. So we all know normal distribution is a continuous distribution having two parameters. one is small m, mean, population mean, and one is sigma. So the situation is same. Capital X1, capital X2, capital Xn is the population of size capital N, and small x1, small x2, dot small xn is a sample of size n. Now what is our target? Our target to find is to the parameter maximum likelihood estimator of the parameter small m and sigma. So you all know that the probability density function for the normal distribution is this, where x should lie between minus infinity and infinity. Okay, let us define likelihood function. If you follow the previous example, this is very easy to write. X1, x2, xn are taken from the sample. So just put on the uh, probability density function and we will have the maximum likelihood function. Taking log both sides, this will be the expression. And of course, since we need to find out the maximum likelihood estimator of small m and sigma, we will make del m of log L equal to 0 and del sigma of log L equal to 0. So just see the calculation. This calculation is not very complicated. You should calculate yourself that small m equal to x bar and sigma square equal to s square. They are the maximum likelihood estimator. Now I have taken some problem which is very important for the exam, that if capital T is an unbiased estimator of theta, prove that number 1, root over T is a biased estimator of root over theta, and root over T square is also biased estimator of theta square. You need to understand the problem first of all. It is given to you that T is an unbiased estimator of theta. That means what is given to you? That is expectation of T equal to theta has been given to you. So what need to be, I need to prove that root over T is a bias estimator of root over theta. That means you should calculate E of root over T, and this should not be equal to root over theta. And for the problem number B, T square is also a bias estimator of theta square. That means you should calculate again E of T square, and which will not be equal to theta square. Let me see the solution. T is an unbiased estimator of theta, so E of T equal to theta. Now just calculate var of T. If you know the formula of variance, var of root over T equal to E of root over T square minus E of root T square. Very simple formula. After that, this will look like this. Since T is an unbiased estimator of theta, E of T equal to theta, just put the value. Yes. Now this will gives you E of root over T. I already told you for problem A, we need to calculate E of root over T. Now see, E of root over T equal to theta minus var of root over T under root. So since variance is always a non-negative quantity, so we can easily say that E of root over T never be equal to root over theta, which shows that it is a biased estimator of root over theta. Again, just calculate var of T, put the value of E of T, calculate E of T square. Since var of T is non-negative, we can say that E of T square not equal to theta, then T square is also biased. Okay, one more problem. If capital X1, capital X2, capital X3, capital X4, capital X5, capital X6 are independent simple random sample of from a normal population with unknown variance sigma square, find out K so that this thing is an unbiased estimator of sigma square. First of all, understand the problem. A sample size of 6 has been given to you. A sample size of 6 has been given to you, and there is an unknown parameter sigma square. The question is that variable, that it is a statistic, nothing but it's a uh, function of the sample, so it's called statistic. This statistic is an unbiased estimator of sigma square. So what we can say, that expectation of this statistic is nothing but equal to sigma square, since it is given unbiased. Okay. X1, x2, x6 is a sample of size 6, as I already told you. Next, they are equal to m. If you see the previous problem, it's very easy to calculate that expectation of x1 x2, they are all equal to mean. Of course variance will be equal to sigma square. Now sigma square is also equal to e of x minus m whole square, that is e of xi square minus m square. So from that expression we can easily write that e of xi square equal to m square plus sigma square. So now calculate the first expression e of x1 minus x2 whole square. It's a minus b whole square formula. Then e of x1 square minus 2 twice of e of x1 into e of x2. In the bivariate random variable we have already seen that if x1 and x2 are independent random variable, then e of x1 into x2 is equal to e of x1 into e of x2. So after all the calculation, e of x1 minus x2 square will be equal to 2 sigma square. Similarly, e of x3 minus x4 square equal to e of x5 minus x6 whole square is equal to 2 sigma square. So all the expressions are equal to 2 sigma square. Now what is given to you? That statistic is unbiased estimator of sigma. So expectation of this thing equal to sigma square. Okay. Yes, expectation of this thing equal to sigma square. So k will be outside because k is constant. So k into expectation of this variable equal to sigma square. Okay. Now according to the previous results, k into 2 sigma square, 2 sigma square, 2 sigma square equal to sigma square. Obviously k equal to 1 by 6. Okay, k equal to 1 by 6. Now the next topic is interval estimation. I will just give you the definition of interval estimation and I will discuss it in the next lecture. So just see the what is interval estimation. Theta is a population of T1 and T2. I already give you the definition. T1 and T2 are two different statistic. Theta is a population parameter. So our basic target will be to find out the interval T1 comma T2 with the confidence of 1 minus epsilon, where epsilon is a positive quantity. So actually it is called if probability of T1 less equal to theta less equal to T2 equal to 1 minus epsilon, if this quantity is valid, then we can say that if epsilon equal to 0 0.05, 0 0.01, 0 0.001, then 1 minus epsilon becomes 0 0.95, 0 0.99, 0 0.999. Then in words we can say that it is 95%, 99% or 99.99% confidence interval. That what is the interval? The interval is T1 comma T2. Anyway, we will discuss this later in the next video. Thank you.